Good evening, sir. Today our topic is vertex cover problem. Our teammates are me, Saniya Ghosh, and Sanket and Sangam. Uh, Next slide. Next slide. Today we will discuss vertex cover, approximation algorithms, optimization problem, approximation ratio, finding approximation for vertex cover, another algorithm, TSP starting point, types of vertex cover, all the summaries. Let's start. Next, let's start with the vertex cover problem. So what is vertex cover problem? Vertex cover of a graph is a minimum set of vertices which cover each in the graph, each edges in the graph. So we can see in the picture that there is a graph which is has A, B, C, D, E, F, and G vertices, and edges are A, B, A, B, C, D, C, E, D, E, E, F, and D, E, and D, G. Now we will consider the degree of the highest vertex. Uh, Now we can see that the D vertex considered the highest degree, so we will remove it first, and then consider again consider the highest degree of the remaining vertices. Then we will see that there is a vertex called E, and we will continue the same process further. And now thus we can find our vertex set of vertex. And next part will be covered by Sanket.
Good evening, sir. Myself Sanket Ghosh, and now I am going to discuss about the topic approximation algorithms. So, the approximation algorithms are the algorithms which use to find near optimal solutions to optimization problems, where finding the exact optimal solution is computationally hard or infeasible. Those algorithms also provided us a way to get a solution that is fully guaranteed to be close for the best possible one within the same factor. So there are the types of algorithms. The first one is greedy algorithms. These build the solution step by step by choosing the locally optimal choices at each step. The another one is local search. This involves starting from an initial solution and iteratively improving it by local adjustment. For example, we can say that in TSP, traveling salesman problem, the local search might involve swapping the order of visits to find the shorter path. The third one is primal dual methods. Those methods are used in problem and like set cover or vertex cover, in which we solve a relaxed version of the problem and refine the solution. So the another next topic is the next slide is optimization problems. The optimization problems are the mathematical problems which are the goal is to find which goal is to find the best solution from a set of possible solution according to some objective function. The best solution is usually defined by maximizing or minimizing some quantity such as profit, cost, distance, or efficiency. Those problems arise in a wide variety of fields, including operations research, economics, engineering, computer science, and logistics. So we can see that there are some key categories of and examples of optimization problems like the types of optimization problem. You can say that the first one is linear optimization. In this case, the objective function and the constraints are linear, and those problems can often be solved efficiently using algorithms like the simplex method or interior point methods. And if we discuss about the knapsack problem, there we can say that a set of items with weight and values, we need to determine the maximum value which we can carry in a knapsack of limited capacity. So the next one is approximation ratio. Sangam, the approximation ratio is a measure of how close an approximation algorithm solution is to the optimal solution for a given optimization problem, and it provides a guarantee on the quality of the solution that the algorithm can produce. For minimization problems, we can see that in there the main goal is to find a solution with the smallest possible value. And as example, we can say that the approximation ratio is 2, and it means the algorithm solution will be more than twice and the cost of the optimal solution. So now, Sangam, please discuss about the next slide.
Okay. Okay. So, good evening, sir. My name is Sangam Raj, and now my topic is finding an approximation for vector cover. So, as it's written that take the idea from the clever exponential time algorithm, but instead of checking which of u comma v a good idea to add, just add them both. While G still has edges, means G here points to a graph. Choose any edge u comma v, add u to Vc and v to Vc, delete u v and any edges touching them. End of while loop. And now the next slide is about the it is about the traveling salesperson uh, algorithm, and the traveling salesperson algorithm, it's a classic combinatorial optimization problem where a salesperson must visit a set of cities exactly once and return to the starting point, minimizing the total travel cost. And the approximation algorithm for TSP, TSP is NP hard, so exact solutions are infeasible for large instances. However, good approximation algorithm exist depending on whether the distances satisfy the triangle inequality. So the first one is metric TSP, which is triangle inequality holds. If distances satisfy the triangle inequality, then Christophite's algorithm says that find a minimum spanning tree of the cities, find a minimum weight, perfect matching on odd degree vertices, combine both to form an Eulerian circuit, which is then shortcut to remove repeated visits, guarantees a 1.2x optimal solution. Double tree algorithm computes an MS tree, minimum spelling tree, doubles every edge to create an Eulerian circuit, shortcuts repeated nodes, guarantees at most two raw into optimal solution. And now another one is heuristics for large instances. For large scale TSP, heuristics provide near optimal solutions. Nearest neighbor, greedily select the closest unvisited city, simulated annealing or genetic algorithms, randomized optimization techniques, and lean Kernighan heuristic, one of the best practical heuristics based on k-opt swaps. And now TSP starting point, which we have like already discussed, and the and next one is hardness of vector cover. So the vector cover problem is NP hard and inherits hardness from the set cover problem. However, due to its vector constraints, it can be even harder to approximate in some cases. And the first hardness result for vector cover, the first one is NP hardness. The classical set cover problem is a special case of vector cover where each vector has binary value 0 or 1. Since set vector is NP hard, vector cover is at least as hard. Logarithmic hardness of approximation. The set cover problem is logarithmically hard to approximate. It cannot be approximated better than big of log n until p is equal to np. Since vector cover generalizes set cover, it also inherits this big of log n hardness in general cases. And then I would like to discuss about the summary, which is understanding your problem really well. Make sure you are not solving an easy special case. Prove the problem really is NP hard. Try a band aid, SAT library, integer programming library, etc. Try to find a good enough exponential time algorithm or an approximation algorithm. And thank you so much, sir. This was all from our